Okay, team, let's take a look at the project deliverable 4. This is your final deliverable for the hydrologic modeling project we're working on in this class. And you're going to submit a full technical report now. And we'll go through the outline of the report, and then we'll get into a few, basically 3 major items that are going to be a little bit of new analysis that you'll do in this project to round out the modeling effort and apply the results. So this report is going to be kind of a typical technical report. You'll have a document heading and title, and then you'll have major sections. And so here are the sections. We'll go through them briefly. Let's have an introduction. This can be from your part 1, where you introduce the watershed, the setting, here are the properties of the watershed, and then give a rationale. Why are we doing this project? What are the design considerations? Maybe take a look at Google Maps again and kind of see what is downstream of the watershed you're working on. Why might we be interested in modeling peak discharge and volume as well? Provide a site map with the watershed boundary under aerial imagery. That could be from stream stats. That might be the easiest way to do that. You could export the watershed from stream stats and import it into Google Earth or ArcGIS if you know how to use that. All right, so the introduction kind of sets the stage. Here's the area that we're working in. Here are the properties of the watershed. Then we can get into data and methods. That'll be the second section. And under this section, ideally, you've already written a lot of this from the previous section. So in each kind of step of the project, I asked you to do a real succinct write-up of your methods. What did you do? And what methods did you use within each component of the model? So we'll have a subheading for each model component. The first one would be, let's see here, data methods. I guess you could give some more detail on the watershed itself, so the drainage area and that kind of thing. The MET model would probably be the next one. So what meteorological components went into this? For each section, you'll have a paragraph that gets into the details of what are the kind of parameters, input data that you used, what methods did you use. We'll want to cite all those things. And then you might provide some summary tables to show, okay, for example, for the meteorological model, we modeled these different frequency and duration flood events, right? So we did the 1% flood, 10%, and I don't know, maybe 50% annual exceedance flood, and then we did these 1, 2, 3 durations for each of those. So that could be a nice table that you would put in here. As far as writing up the methods, let's be very specific. We want to document every kind of input parameter and data that you used in every method. So here's just an example of what you might consider for the MET model. Where did you get your rainfall depths from? What frequencies did you use? What points to area conversion method did you use? And then what design storm hyetograph method did you use? So you can just kind of go through the MET model, and we can pull that up over here. So I've got HMS open, and I click on the MET model. We use the frequency storm. Here is the storm type. You can kind of look that up in the methods manual if you haven't already. Do we do an area reduction method? Yes, that's TP40. Let's cite that. What intensity position did we model? And then these kinds of things you're already going to be summarizing, right? We don't need to get into this detail, but that's the kind of basic information. So we used a uniform curve for all subbasins, and that's based on I believe the area reduction method. So very detailed, right? If someone is checking your work, like your supervising engineer, or if this report goes out to a regulator or something like that, we want to make sure that you've covered all your bases and you've documented everything. Let's be very specific in the each method and data source. So for the curve number, I give you an example here. This is a very pithy way to do it. We said, okay, we use the SDS curve number method to model rainfall runoff volume, also known as the loss method in HEC HMS. The curve number for each subbasin was estimated using stream stats, right? You didn't do it manually. Stream stats utilizes the following data sets to calculate an area weighted curve number. following NRCS 1986. That's the curve number method. And then be specific, right? Where do we get the land cover information from? You're going to have to dig in, if you haven't already, dig into stream stats and understand where that data come from. And you might need to go back to, I think it's the second part of this, no, it's going to be the third part of this project to get some more information on that. Ideally, you've already documented this, right? I asked you to write up a nice pithy paragraph documenting your work and your methods for each one. Use tables to summarize input parameters. We don't want to say in a sentence, subbasin 1 had a curve number of 65 and subbasin 2 had a curve number of 82. We want to just summarize that stuff in a table and then just refer to the table. And this, I think this is complete, but this would be a table that could summarize your subbasin parameters used in HEC-HMS. All right, so each method and kind of component of the model is going to have a subsection. So meteorological, subbasins, reach models, right? Those will all have subsections to them. Now we'll write about the results, and this can be very succinct here. Describe the results in general, just do kind of a paragraph narration of your results. And then we'll have graphics, so plot your hydrographs. And this can be, you can graph them on top of each other, right? Based for the different storm events and durations. So maybe you have a graph, a 1% storm event with the different durations, right? I think we did 3 different durations for each frequency. And you could have 3 graphs, let's say, where you have one graph with the 3 different durations for 1%, for 50%, et cetera. Provide the results in a table as well. This can be one table. So we have maybe frequency as rows and then durations as columns and then peak discharge and volume. You can have a table for peak discharges and a table for volumes of runoff. Maybe there's some other figures. So let's just describe this. You kind of, the tables and figures will be the most important thing to convey the results, but you also want to have a little bit of description in there as well. Then we'll have a section for the sensitivity analysis. This is going to be a separate results and discussion section. And we'll talk about the sensitivity analysis in a second. The second to last section will be design, and I've got some questions and methods that you'll apply the results to do some design calculations. And we'll basically just report the results of that there. Finally, in your conclusions, just summarize what you did. We used HEC-HMS to model peak discharge values and volumes for a range of frequency flood events and durations. We found that the maximum peak discharge came from this flood event with this duration. And we connected the sensitivity analysis. We found that this parameter, the model was, the results were most sensitive to this particular parameter. And finally, we apply these results in a design. One paragraph just summarizing what you did. I will be looking for internal citations. Any data or method that you use that requires a citation. So internal citations and then a reference list. Finally, we'll have an appendix, and this can be where you bring in information from the previous project components or project submittals. And maybe there's some example calculations that you've documented. That kind of detail you can put in an appendix. We don't need every little method and every little equation in your report. 10 out of the 120 points for this submittal will be based on formatting, grammar, your ability to reference things internally in your reference list, and the quality of your figures and tables. I have posted a rubric on Canvas, and we'll take a look at that in a second. Actually, let's take a look at it now. Why not? Here's the rubric. It's posted under the project. I'm going to be using this to grade it. So just take a look at the full points for each of these topics, and I'm just going to be grading each section as you go. All right, 10 points for grammar and presentation, 5 points for references. So this can be your guide. Just take a couple minutes to read this before you start writing. Now let's take a look at what you're going to be doing, kind of the new stuff you're going to be doing for this project. You will be running the various MET models, and this is a typo here, but you'll have, I believe it's 3 MET models, so the 1 hour, 6 hour, and 24-hour duration storm events. And then for the 1% flood, I think we did the 10% and then 50%. Actually, sorry, let's take a step back here. We're only going to be reporting the results for the 1% here, because that's going to be the one that we care about the most. That's the biggest flood event. So we'll have the 1% frequency flood, and then these 3 durations. That's going to be based on initially the 50% storm intensity position, and we will look at the sensitivity analysis in a second. Where do you get this information? Well, let's go to HackHMS and take a look. So we've gone through all the steps, and in the part 3, you actually went and ended up computing some model results. So under Compute tab and Simulation Runs, we click on this particular event, the 1% AEP flood. This is the 1 hour duration. And let's see here, make sure we get some results. This shows the kind of the simulation run. And then under results, we can find the results based on a particular computation point. So we made sure that our junction was a computation point by right-clicking on it and making it so. And we'll talk about running it for a subbasin as well. But that means we get results for the junction. So I'm going to click on junction 1. That's my outlet. And I'm going to actually, under results, I'm going to click on that. And I have my results here. So result tab, I can click on graph and see my hydrograph that comes out. I can click on summary table, and this gives me the peak discharge in CFS, and it gives me my volume in inches or acre feet. And then I can get my time series table. So this is where you could plot your hydrograph. So if I, let's see, I think I can just select this by dragging and dropping, or maybe I press Control A and select everything, Control C. I should be able to plot that into Excel and overlay different hydrographs and plot them together. And I'm interested in the outflow, right? The inflow would be all the different hydrographs coming in. The outflow is what I want to plot. So that's going to be the main results that we want to report for the model for the whole watershed. I'm just going to go back to my basin model here to plot that. Actually, we'll just X these out here. Okay. So there's my watershed model. And for the main results section, again, we'll just report the 1% flood. I think we'll just stick to that, and that'll be the most streamlined reporting there. You could imagine a project where maybe you needed to model the 1% flood, but then there are some modeling components or design components that dealt with the 10% flood or something like that. So we'd, in that case, report those different flood events. All right, let's talk about the sensitivity analysis. We know in the modeling and kind of all the things we've been talking about that there's a lot of sensitivity and, or sorry, uncertainty in the input parameters and the methods that we use here. A lot of them are based on kind of empirical methods, regression equations, kind of mean results. So let's take a minute here to consider how sensitive our results are to uncertainty in the inputs. We're going to look at 3 different things. We're going to look at the storm intensity positions. So this is part of the MET model or the meteorological model. We'll look at the curve number uncertainty and then our lag time uncertainty. And these are part of our subbasin model. Let's take a look at our storm intensity position. If I go back to model components and under meteorological model, I want to change the storm intensity position and see how that changes. And so that storm intensity position is basically where does our peak fall in our hydrograph? Does it fall in the first 25% of times? Does it fall in the middle, or in the last 75% of time? So for a 6-hour duration storm, if I select, let's just go look at that for a second. So I'm going to go to our meteorological model, I'm going to click on frequency storm, and then I'm going to look at the intensity position. So I can do 25% or 75% or something in between. All right, so I'm just going to change that, save the model, run it, and then we'll just do that for the, I said for the 6-hour storm. Sorry, let's go to the 6-hour storm event, run that, we'll change it to 25%, run the model, and then see how it changed your output. But in order to kind of compare everything, the curve number, the lag time, we're going to just calculate this based on one subbasin. So I'm going to choose one subbasin, let's say subbasin 4 in my case. I'm going to right click on that. I'm going to select computation point. Okay, when I do that, I get a little red dot on it. That's a good thing. We want that little red dot. I can also make reaches computation points if I want to do that. Select computation point. And what that means is that when we run our model, we're going to get hydrograph outputs for that subbasin as well as the outlet. The outlet is a computation point. We care about that, but we're also going to get within a subbasin, we're going to get some results. Okay, so I made that a computation point. Then I go back to my meteorological model. I said do it for the 6-hour duration storm. So let's click on that. Intensity position 25%, run the model, get your hydrographs out, get your results out, right? The volume, the peak, and then go back and change it to 75%, run the model, get the hydrographs out, the volume, the peak, and that's going to be what we do for this sensitivity analysis. All right, does the position of the peak actually change? It's not going to change the volume, right? We don't expect to change the volume, but it might change the peak discharge value. All right, that's sensitivity analysis for storm intensity position. Now let's look at these other components. The curve number. So I select subbasin 4 as my computation point. I'm going to go back to that model, subbasin 4. And I want to change the curve number. I'm going to say if the curve number uncertainty is plus or minus 10%, that seems like a reasonable uncertainty range. Let's click on the loss tab. So my curve number for this basin is 50, in which case I would make it up. We're going to do plus 10%. That's going to be 55. So I'd save that, run my model, go to results, get the graph out for subbasin 4, right? Get the summary table, or the time series and summary table. I want to get the hydrographs out, and I want to get the peak flow and volume out just from subbasin 4. You can imagine that I could do the sensitivity analysis for the whole watershed, but I have to go change everything, each subbasin, plus 10%, minus 10%. So I'm just trying to make this a little bit easier for you. We'll just do one subbasin. So again, I'm getting the results out of subbasin 4 because I made that a computation point. Notice that subbasin 2, I didn't make that a computation point. It won't have any results in it. All right, so that's curve number. I can go back to components, subbasin 4 loss. And so I make that 55, that's gonna be plus 10%. We'll do 45 minus 10%, all right? So we'll run that and then we'll compare it to the original subbasin 4 value of 50. And then the last thing we'll compare is the lag time. So that's gonna be our under transform. So lag time, again, we'll do plus or minus 10%. So if my lag time is 60, then I'm going to do 66 minutes for plus, run the model, and then I'm going to do 44 for minus 10%, and then run the model. And so what that ends up doing is we'll have a series of hydrographs. We'll have a hydrograph for the plus 10% lag time, hydrograph for the minus 10% lag time, and you can compare those. Compare them in terms of the peak discharge and the timing. Really, we're probably mostly interested in the peak discharge value. And you can see if that is, how big of an influence that is, right? If we did plus or minus 10%, what does that mean for the peak discharge? Is it plus or minus 10%? Is it 20% difference, right? From the range of uncertainty between those two peaks. So for each parameter sensitivity, include a graph and plot them on the same graph. have a table summarizing the peak results by scenario, and then describe how sensitive the results are to the parameters being studied. All right, we're going to do this for this particular storm event. That's going to be the one we're comparing everything to. And we don't want to change multiple parameters, right? So for the curve number and lag time method, just use this storm event with the 50% intensity position. We're just changing one variable at a time. And then, so compare the hydrograph peak and volume at the watershed outlet in relative terms, so percent of the original, and that's going to be just for this particular subbasin that you're working in, okay? Not for the whole watershed. And then now let's think about this in general. If you're designing a critical infrastructure, how would you address uncertainty in your modeling to inform your final design? What methods would you use? Would you do this kind of sensitivity analysis? And then what final answer in terms of peak discharge or volume would you use? Then what other parameters out there could influence the results that we didn't study? Are there other parameters that go into the subbasin that are important, that might be uncertain? Are there, think about the meteorological model, and then think about the reach model, because we didn't do sensitivity analysis for that. All right, the last part of this project is the design, and there's two design questions here that we'll look at, okay? The first one is a culvert. So say this watershed outlets to a culvert. In the case of Canna Creek, we outlet to US Highway 50. So there's a culvert that Canna Creek runs under. And then we're gonna do a very basic culvert design, all right? We're gonna say it's a box culvert, and we want to assume open channel flow and normal or critical flow depth, whichever is greater. So we'll use Manning's equation to calculate that. And then we're gonna want 1 foot of freeboard. This is gonna be based off of the peak discharge. So the 1% AEP, whichever duration results in the biggest peak discharge. And it might be the short duration or maybe the long duration, I'm not sure. You have to figure that out based on your model results. So once we know that peak discharge, we want to design the culvert so that we have 1 foot of freeboard, meaning 1 foot of headspace above it. And so what are the dimensions of that culvert? You could assume it's a square, that's fine. And then assume a bed slope of 0.5%. So use Manning's equation. We'll assume open channel flow with Manning's equation. We're not doing the kind of culvert head loss type of calculation that we did in hydraulics. This is a simplified approach. Designing a real culvert, we have to go through those head loss steps of flow through a culvert. And we covered that in open channel hydraulics. You can refer back to your notes for that. Okay, so how big is that culvert? We need to know a width and a depth. There's going to be different ways to do that. You could say, I'm going to just say a 10-foot width and then calculate your depth based on that. You could do some iterations on it to figure out what's the kind of optimal design for that. The last calculation we'll do is a detention pond. And we're going to use a very simplified method. This is basically a triangular hydrograph method. And the volume, this is basically going to say that we have an inflow hydrograph, an outflow hydrograph, and the volume of the pond is going to be based on the difference in volume between these two hydrographs. So there's water coming in, there's water going out, and this is what water is in storage over between the inflow and outflow. So I gave you some basic assumptions. Here's the method right here. Here's the design equation. We're going to assume that the peak flow of the outlet hydrograph, QA, is 50% of the design inflow. Okay, 50% of the peak discharge. And then calculate the base time as the time between the initial hydrograph rise to when it falls down to 10 CFS. That's going to be on your hydrograph, the hydrograph that you calculate at the outlet of your watershed. And we're going to do that on the 1% AEP hydrograph that creates the biggest peak discharge. So that'll be your base time. And those are the parameters you need. So the volume of storage, is going to be equal to 1/2 times the base time right here, and then the difference in peaks. Okay, so that will give you your volume. Check your units, right? Make sure, you know, if you're cubic feet per second, is this time in seconds or hours? And then make sure that this volume is something that's meaningful. Okay, cubic feet or acre feet or something like that. All right, so that'll be the volume of a detention pond. And then I'm going to have you guys refer to the Grand Junction Stormwater Manual, and we're going to look at detention and retention ponds. So take a look at that section, read it, and then answer these questions. And that'll be the kind of discussion that you'll have for the design right up at the end. So that's what you'll be doing for the final project. Again, make sure to read through these sections, read through the rubric, and make sure you get kind of a nice, succinct, right? Shorter is better, but detailed right up here, so that we can kind of submit this. And this would be very similar to what a design or consulting engineer would submit for their hydrologic analysis part of any sort of design problem.